Okay, well, I don't know if I really want to do this problem. I think this is the same one that's in one of the examples that's in the book, but actually it looks a lot like it's going to be a Shams outline problem. I guess maybe I'll do it. So this is example 3 of class 21. And we will have the spool and a telephone wire is wrapped around the top of it. And this thing has a total mass of 80 kilograms. And they give us a radius of gyration of 0.3. So we have a coefficient of static friction between the spool and the ground is 0.4, and the coefficient of kinetic friction is 0.2. And we're going to determine the angular acceleration of the spool if the end of the cable is subjected to a horizontal force of 30 newtons. This is sort of an interesting problem because we sometimes might get confused as to which direction this thing is actually going to rotate. It's kind of a cool demonstration, but I don't have the spool that I used to, which was kind of a cool in-class demo. We get the moment of inertia just from that radius of gyration, and we have to ask the question as part of this, will it slip, right? And that's going to be determined if the friction force is going to be less than so if the friction force is less than the coefficient right here, this 0.4 of static friction times the normal force, then it won't slip. But if the so in that case, if it doesn't slip, the coefficient of friction is 0.2 times the normal force. Or no, I guess if it does slip, yes, okay. And if that happens, then the velocity of the floor does not equal 0, right? So then this is not a instantaneous center. So we did the FBD in the IBD, and I'm assuming that it's going to be rotating about this point right here, and I have the angular acceleration going in that direction in accordance with this, right? So if I take the sum of the forces in the y direction, it is not moving upwards, so they have to be 0 right here, the sum of the forces in the y direction, because there's no velocity in the, no acceleration in the y direction. It can't. So some of the, so we get what the normal force is going to be. And so now we know what the criteria is. If the friction force that this thing is experiencing right here is 13.9 newtons, if it's less than that, then we're going to have no slip. But if it is slipping, then the friction force is going to be 157 newtons. Now take a look at the x direction right here, and that we're going to find the relationship between that friction force, as we see up here, and the 30 newtons that we're pulling. Those two things are both in the positive direction, and that's going to equal 80 times whatever the acceleration ag is going to be. So we also can take the acceleration, take some of the moments about the center of gravity, g of this thing, and then the alpha, right? So now if we do that, we're, we will see that this force is going to play a role, and that's going to be because we're taking it about this center. But then we don't have to worry about the effective moments here, because we're taking it about the center, and this passes through it. So all we see is that Ig alpha right here. So that's what we have. So we have the friction force, and we have the alpha right here. So those are really the three unknowns right there. Wait, three unknowns where we have we have the acceleration of g too, right? So three unknowns and two equations. But okay, so if there is slip, right? If there's no slip, I should say, then the angular acceleration and translational acceleration are related by this. That is not true if there is slip. But that's what it's going to look like. It's going to be we're going to pretend it's pinned right there, and these two things will be related to each other. And so we go ahead and we put in that relationship, and what we get out an angular acceleration here, and then we can find what the friction force is, and we determine that the friction force is much less than the static force, right? The static friction, right? This would be what it needs to overcome that for there to be slip, right? So if you were to pull this hard enough right here, there would be slip, is what we're interpreting that to be. So we get alpha to be 0.546. And then we go to this what if scenario right here. It's like, what if the rope was wrapped in the opposite way? Well, we would take all the same things, except that now there's going to be a different moment taking place, and we also are going to assume no slip. So we go in the x direction, we get that same relationship. Now we have to be careful here. We notice that this right here is the sign changes. So that's really the big difference right in there, right? We still have over here, we're taking it about G right here, and we still have this right here in the in the clockwise direction. And again, if there's no slip, we have that AG. And we apply all these things in here, and now we get a negative 11.03. And it's interesting, though, that it's in the negative direction, right? So that friction is actually sort of like pushing this thing along. So I'll move on to another problem here in the next video. That actually, I should mention, is a topic that comes up here, right? So you could work through, and you could see this is really this problem, I should point out. I think I ended up in my notes from another instructor, or I was watching another instructor's class, and they were using that in both ways. But it's a good one to work through. But also notice that it is in the book.